Okay, now that you have a better grasp on the properties of electricity, that is the voltage, the current, and resistance, let's look to see how we can calculate these three parameters in a typical circuit. So in this schematic, we have a battery up here. Got a battery. So the large plate and the small plate is a symbol for a battery. We have the plus side on the left and the negative side on the right. So we now have a driving force for the electrons to go through the circuit. So the current coming from the battery will be the same throughout the circuit. The current coming out of the battery, the current going through the resistors, either resistor, is going to be identical. From our water analogy earlier, it is like connecting two hoses together, two hoses back to back, and then you connect them to the bottom of the tank. The same is true in this circuit. We've got a voltage source pushing the electrons through, and then we got two resistors back to back. So the flow coming out of the battery is the same flow that's going through the first resistor, and it's the same flow as going through the second. So we call this type of circuit a series circuit. In other words, the circuit elements are back to back or in series. Okay, let's take that same circuit that we had before, except replace the resistors with light bulbs. Everybody can relate to a light bulb. You would expect that the more light bulbs I put in a row, the dimmer they're going to get, right? Well, why are they getting dimmer? Well, that's because the current is getting less and less through the circuit. So if the current is getting less, we must be adding more resistance to the circuit. And that's exactly what happens when you have a series circuit. The more elements you put in that circuit, the more resistance you're going to get. So the circuit resistance is additive in this series circuit. That means that the more light bulbs we add, the higher the resistance. In fact, it's a linear relationship. For each resistance we add to the circuit, the total circuit resistance would be the sum of each individual one in the circuit. So it would be whatever resistance lamp 1 is, plus 2, plus 3 is the total resistance that the battery has to push the electrons through. All right, now let's rewire our circuit, and let's put the light bulbs in like we have shown on this schematic. So we got three light bulbs and one battery. Let's think about our water analogy first. How is this similar to the water analogy? We got a tank of water. The hose is coming out of the tank, and then we put in a T, in this case a three-way T. So the water is going to flow down one hose, a second hose, and a third hose, recombine, and then go back, well, actually onto the ground as far as the water goes. All right, so the same is true in this circuit. We're taking our voltage source and we're tying it to all three of these light bulbs. We take the three little light bulbs, we wire them together, and then we wire it to the battery. So the voltage at the top and the voltage at the bottom is the battery voltage, the 24 volts that we have here. So just like in our water analogy, we're going to split the current that is coming out of the battery into three streams, one going down lamp 1, 2, and 3, right? Then we're going to recombine it and then take it back into the battery. So to just give you an example or put some numbers to this, let's say we got 3 amps coming out of the battery. Let's say each one of these light bulbs has the same resistance. How many amps would I get going through each one of these light bulbs? Well, that's correct. The answer is 1 amp. So we got 1 amp coming into here, 1 amp here, 1 amp here. Recombine them, I get 3 amps. The voltage across each of these lamps is identical, but then the current splits. This is called a parallel circuit. We are taking the elements in our circuit, we have a common voltage at the top, common voltage at the bottom. In this case, we have 24 volts at the top and we got 0 volts at the bottom. So again, this is a characteristic of a parallel circuit. The voltage is common across the element in the circuit. All right, again, we're back to a series circuit. So this means the current flowing through the circuit, the current going through the 10 ohm resistor, the 25 and the other 25 is identical. That was our definition of a series circuit earlier. So how much resistance is in this circuit? What is the total resistance? How much resistance does this battery have to push the current through the circuit? Well, it would be the total. By total, I mean you add up the 10 ohm, which is the first one, to the second one. So 10 plus 25, we're up to 35, and then we add the final one, which means we're up to 60 ohms. So this battery is looking at a resistance in the circuit of 60 ohms. If we were to take this 10 ohm resistor out, does the total resistance increase, stay the same, or decrease? Well, it's pretty obvious. It decreases, right? So instead of being 60 ohms, it's going to be 50 ohms. If it's 50 ohms and we don't change this voltage, what's going to happen to the current? Well, it's got less resistance, so the current has less resistance, has the same voltage source pushing those electrons through, then the current's going to get higher, right? All right, so now you're getting the feel for the series circuit has a common current going through it. The amount of current is going to be based on the resistance in the circuit, and you just add up the elements to get the total resistance. Okay, we clearly see there's some kind of relationship between the 3 electrical parameters, voltage, current, and resistance. A German scientist back in 1827, his name was George Ohm, figured out this relationship. He's one of the first ones that had figured this out. So he said that if I were to double the resistance in a circuit, the current is going to drop by half if I keep the same voltage. That's what we mean by linear. So if one goes up, one goes down. All right, so he came up with the equation, and obviously it was named after him. So we call it Ohm's law. It's not really a law, it's just a relationship. All right, so he's saying that volts are equal to current times resistance. That means we got 3 parameters. If we know 2 of the 3 parameters, we can calculate the third. So in this first equation, if we know current and resistance, we can get the voltage. All right, now using a little bit of algebra, we can rewrite this equation and solve for I. So current I is equal to voltage divided by resistance. Or if you solve it the other way around, for resistance, resistance is equal to voltage divided by current. So this basic voltage is equal to current times resistance. That's called Ohm's law. And again, you only need to know two of the three parameters to figure it out. Now, if you're not good at algebra, that's why I'm drawing this circle up here at the top. So take a circle like this and divide it into two sections. Put a horizontal line this way, a vertical line that way. Now, assume the horizontal line means divide, okay? Assume the vertical line means multiply. You don't have to put the divide and multiply sign, but I'm going to do it the first time just to clarify what we're talking about. All right, so our first equation, V is equal to I times R. Well, we get that in a circle by saying V is equal to I times R. All right, the second equation, we're going to solve for I this time. So I is equal to V divided by R. And the last one is, if we are going to try to solve for resistance, V divided by I. Now you're going to see this quite a few times in this course. I don't just mean Ohm's law, but you're going to see three parameters, and we need to solve for one of the three parameters. We're going to use this circle quite a bit in this course. So try to get used to coming up with these two other equations by using this circle here. All right, let's take the circuit that we have shown here and let's see if we can apply Ohm's law to it. All right, first thing you got to recognize is what kind of circuit. Is this a series or is this a parallel? Well, it's obviously a series. The current throughout the circuit is the same. It's the same on the 10, 25, and the other 25. So Ohm's law is going to tell us that the voltage drop across each one of these elements, the 10 or, well, let's just talk about the voltage drop across the 10 ohm resistor here, is equal to I times R. All right, now, it looks like if we study this circuit, we know the voltage, the 12 volts, we know the resistance in the circuit. Total resistance would be 10 plus 25 plus 25 is 60 ohms, right? So if we knew the current in the circuit, then we can get the voltage drop across each one of these elements. So it looks like we can calculate the current because we know voltage, we know resistance. So I, which is the current, is 12 volts divided by the total resistance, which we just said was 60 ohms. 12 divided by 60 is 0.2 amps. So the current through this 10 ohm is 0.2, 25 is 0.2, the other 25 resistor is 0.2, and back into the battery is 0.2. All right, now what is the voltage drop across this first resistor? Well, if the current is 0.2 amps and the resistance is 10, all right, how can we use this same concept now that we have a parallel circuit? By now you should start to recognize that this is a parallel circuit. The total current coming in is going to split three ways, right? I1, I2, and I3. So the common element in this parallel circuit is not the current like it was in the last circuit, but it's the voltage. We got 12 volts across each one of these resistors. So let's take a look at how much current is going through this first leg here, which is I1. So we got 12 volts divided by, well, the equation, I is equal to the voltage across V divided by the resistance. The voltage is 12. So 12 divided by 10 ohms is 1.2 amps, right? Going over to the next one, it's same voltage, 12 divided by 25 ohms. And again, lucky for us, the same resistor, so the current must be the same amount. So again, 12 divided by 25 is 0.48. So you sum up all three of those. You take the 1.2 plus the 0.48 plus the 0.48, and you end up with 2.16 is this total current back here. All right, another way to look at this is if we knew what this total resistance down here was, then we could have calculated I, because I is equal to V divided by the total resistance. All right, now in this case, it's a little bit trickier to figure out the total resistance. But go back to the water analogy. If I had three hoses here, and each, let's say these two 25 ohm resistors represent a small hose, the 10 ohm represents a big one. The total resistance for the whole circuit, I got three ways for this water to go through this path here, right? So the total resistance is going to be less than even the biggest hose that I got. So use that when you are calculating the resistance. Now the equation to actually calculate the total resistance is shown here on the right. You take 1 and you divide it by 1 over the first resistor, plus 1 over the second, plus 1 over the third. So we take 1 divided by 1 over 10, 1 over 25, plus 1 over 25. So if you're good with fractions, we got 1 divided by 0.1. 1 over 10 is 0.1, plus 0.04, plus 0.04. You add them up, it's 0.18. 1 over 0.18 turns out to be 5.5 ohms. Is 5.5 ohms less than the smallest resistor we got? Sure is. So we must be in the ballpark. So use that fact as a check to make sure that you're calculating it right. All right, now once you have this total resistance, again we said I, in this case I total is going to be equal to the voltage 12 divided by 5.5. Now we're going to end up with the same number, the 2.16 amps that we got previously. So that's two different ways of determining what the current is. We did it individually and then we summed them up to get the total. That's probably the easiest way. Or if you want to go ahead and calculate what the total resistance of the circuit is, then you can use the fact that we take the voltage, which is common across each one, the 12 volts, and divide it by the total resistance. And we end up with that 2.16 amps again. Usually in the lab when you're working on these things, you try to prove that your calculation actually is working out. And by proving it, I mean you use a meter to figure it out. So let's say in this particular circuit, which is pretty simple, right? It's just a battery and a light bulb. We want to know what the resistance is of this light bulb. That would be the eventual goal. But in order to get that, we need to know the current in this series circuit. So we're going to talk about how we measure the current in the circuit now. So you take your multimeter and you put it, this is a DC power supply, so you'd be putting it in the selector switch in DC amps. But this time you put the circuit, you put the meter into the circuit. You break the circuit, you see where it says A here? A stands for the ammeter or multimeter. You put that into the circuit. So the current that's coming out of the light bulb, you pass it through the multimeter and then back into the battery. But you're calculating the I value, then you would go ahead and use this meter to actually prove it to yourself. You'd put the meter into the circuit. Let's see how much you're picking up here. All right, what kind of a circuit is this? That's right, it's a series circuit. The current is common through each of these elements. What kind of a circuit is this? Must be a trick question, right? It's a parallel circuit. So we got current going down through the resistor and a current going down through the lamp itself. The common element in the series circuit, remember, is the current. The common element in the parallel circuit is the voltage across the two that are tied together here. All right, now we didn't talk about this, but I want to make sure to cover it. On your multimeter is usually a section down here that has this symbol that looks like a speaker. That speaker basically is a buzzard on the multimeter. This is a way to check continuity. So if I took a solid wire and I want to make sure it's not broken, another example would be a fuse. But let's stick with a solid wire here. So I put my black and red probes on the ends of the wire, and a lot of times I'm not going to be able to see this display, so I'll turn it to this buzzard location, and if there's continuity, in other words, if the electrons can pass through my meter, then I'll hear the buzzard go off. So it's a good way to use your meter if you can't see the LCD.